So hello students. So in this session we will cover our dynamic analysis part of G plus 15 multi-story building with the help of response spectrum method. Okay, so response spectrum method is a linear method. Okay, and another one is time history method, which is a non-linear method, dynamic method. Okay, so you understood the concepts of static seismic method. Okay, and now we are going to see how these can be analyzed in StatPro. Okay, so for G plus 15 building, we have a problem like this. Now this is a project. Like consider a 15-story reinforced concrete office building. A building is located in Shillong. That is the seismic zone factor of Shillong is 5. The Shillong belongs to zone factor of 5. The soil conditions are medium stiff. Okay, so this is a condition that we have to enter a value of medium stiff in a stat pro, and the entire building is supported on a rough foundation. Okay, and another information in this is the RC frames are infilled with brick masonry. Okay, and the size of the beam is 0.23 meter by 0.4 meter. Okay, and 0.4 meter is your depth and 0.23 meter is the width. Again, your column size is 0.23 meter by 0.45 meter. It is 0.45. It is 0.45, not 45. 0.45 meters. Okay, and the lumped weight due to dead load is 12 kilonewton per meter square on floors and 10 kilonewton per meter square on the roof. Okay, so the lumped weight which is in acting on a structure, the dead load is given as 12 kilonewton per meter square on the floors and 10 kilonewton per meter square on the roof. Okay, so we have to enter these values in the stat pro, and the floors to cater for a live load of 4 kilonewton per meter square on floors and the 1.5 kilonewton per meter square on the roof. Okay, so we know in response in seismic analysis whether it is static or dynamic. We know the imposed load, that is the live load, is acting if our live load is having a magnitude 3 kilonewton, more than 3 kilonewton per meter square. Okay, so it will be acting or it will be imposed on the structure as 50%. Okay, so here so it is more than 50%. So more than 3 kilonewton per meter square, so it is of 2 kilonewton per meter square is acting on the floor. Okay, so likewise we have a value 1.5 kilonewton per meter square on the roof, and we have also in our IS 1893/2016, okay, which is a new code. In that also the 3 kilonewton per meter square, which is the value is 3 less than 3 kilonewton per meter square, then our imposed load either on the floor or the roof will be considered as the 25%. Okay, so 1.5 uh, kilonewton per meter square, and the 25% of 1.5 is 0.375 kilonewton per meter square, which should be applied on the stat roof. Okay, likewise we have a 2 kilonewton per meter square to cater our live load on in a stat roof. Okay, so determine the design seismic load on the structure as per the code. Okay, so this is a problem. Now see, we see in the stat pro. So go to stat pro. Okay, stat pro is taking some time depending upon the configuration of your laptop. Okay, so here I select a new project, go to space and change your name, that is dynamic analysis of G plus 15 building by response spectrum analysis. Okay, so length in unit is meter. Okay, and force in unit is kilonewton. So it is done. Next, then where do you want to go? Then add beam. Okay, by default it is on add beam. So finish. Okay, and here your GUI of StatPro is here, and it is opening. Okay, so first what we have to do, we have this is our isometric view. Okay, so when you hover your mouse on the particular icon, you have your name, the isometric view. Okay, and this is your view from plus z. So from plus z direction we have, so go to directly to make a geometry, go to your uh, structure wizard model, then run structure wizard. Okay, now we are having a model type as frame models. Okay, so we are selecting here as bay frame. Okay, bay frame of G plus 15 building. So if I'm considering 3 meters height, so here length is you have your dimensions with you. That is the length is 20 meters. If I'm considering length of 20 meters, so number of bays along your length is 4 here. So no problem, should be 4. Okay, and height is 15 meters, so it is to be replaced by 45 meters. Okay, and the width is again your 15 meters. So here if I am considering 15-meter width, then number of bays, if I am considering here 5 meters, if my bay width is 5 meter, so 5 3 is 15, so it is number of bays will be your 3. Okay, same here, if your height is 45 meter and if I am considering 3 meters floor, so what is this value? This is your 15. Okay, so 15 into 3, it is 45 meter. Okay, if I'm considering whole structure of 3 meters height. Okay, and if I'm considering of 5 meters in length direction, so 5 into 4, 5 4 is 20, so it is 4, it is correct. Okay, so here you can see these are the three dots, that base of 5 meter, 5 meter, 5 meter, 5 meter. Okay, here, so length of 20 meter, so equally space of 5 meter, 5 4 is 20 here. Okay, so again you can see here it is of 3 meters. Likewise, we have our number of bays along width of 5 meter. Okay, so apply. So this is a model in our run structure wizard. So we have to transfer this model in our StatPro graphical user interface. So click on cancel button. Okay, and the dialog box will come and he asks, would you like to transfer or merge this prototype into StatPro? Yes. So here you press on OK button. Okay, so here it is your model. Okay, so this is our default grid lines. We have to hide this default grid lines, so click on your snap node or beam, so it is for cancel, click on cancel. Okay, so this is our structure, and now here we have to define our beams, we have to define our columns, we have to define our slab of flow. Okay, so first what we have to do, this is our view in isometric view. This is a okay, and so first I create a slab. So go to your front view. Okay, now select your cut section command. Okay, so cut section command, and select to view, and press OK. Okay, and now select your lower portion. Okay, and here you can see the isometric view of this. Now select your plate cursor. This is your plate cursor. Okay, and this is our add four noded plates. Okay, so we choose our add four noded plates here, and after click on add four noded plates, click on four nodes of outer side, first, second, third, and fourth. Okay, so here on first story we created a four noded plates. Okay, so see the whole structure, display whole structure by clicking on this icon. So this is all whole icon. Now select a plate cursor. Okay, if you select a plate cursor and choose whatever you draw. Okay, so this is our plate, it is formed here. Okay, now go to your translation repeat. So it is your translation repeat option. Okay, so translation repeat, and where we have to translate it and repeat in y direction. Okay, so this is a global y direction. Okay, so it's asking how number of steps, how many times we have to copy our base slab. So it is asking auto save, no. Okay, so here you can put your values as 1 2 3 4 5 6 7 8 9 10 11 12 13 14. So type here as 14. Okay, so and default step spacing is 5 meter, no, we have a 3 meter floor to floor height. Press on OK. So all the floors have been created. Okay, you can select all the structure, you can see here. Okay, all the floors have been created. Okay, now go to your general option and go to property. Okay, so property we have to define our beams and define our columns. So go to define. Okay, we are choosing our rectangular beam and rectangular column in our problem. So rectangular beam. Okay, so what is the size of the beam? That is YD. YD is your depth. So we have our depth of beam is 0.4 meters. So it is 0.4 meters. And ZD is your width. So width we have a 0.23 meters. Okay, so add it. Again we have to choose our column. So we have our width is 0.23 meter column and we have our depth is 0.45 meter, okay, in our problem. So add it, close it. Okay, now we have our slab. So go to your thickness. So we have a slab of thickness usually 100 mm to 150 mm we are considering. Generally we took our average value, that is 125 mm slab we are taking. So 0.125 meters. Add it, close it. Okay, now this is your beam, this is your column, and this is your plate thickness. Okay, so what we have to do now, we have to select our beams, and we have to go to select option here, and beams parallel to, where are the beams? So beam are in only x direction and only in z direction. So z direction and x direction we have to select. So beam parallel to x. Okay, so whatever the beams in x direction they have selected, we have selected. And again go to your select option, beams parallel to z. Okay, so z direction beams are also selected. So here assign to selected beam, this is a assignment method. So assign yes, is asking yes. So all the beams have been assigned. And now similarly we have to go to your columns. Then again select option, beams parallel to, now columns are in y direction. Okay, so this is a y direction. So select your y direction, all the columns are selected here. Okay, so now go to assign to selected beams. Okay, that is beam. Yeah, you know, the in Staad Pro, if we have our in x direction as a direction beam, it is a beam, and in y direction it is also called as a beam. Okay, but in y direction we are considering is a column. Okay, so assign to selected beams. Okay, so that's why assign it yes. So assign, so columns property have been assigned. Now go to plate thickness. Plate thickness we have a 125 mm plate. Now go to your, this is our view. So for whole view we have to assign our plate thickness. So assign to whole view, assign to view, assign yes. So all our properties have been assigned, like beam, column, and slab. Now we have to choose our supports. So go to your Z plus Z form view. Okay, select your support. Okay, now go to your, we have to add our fixed support. So create it. Now we have a fixed support here. So add it. Okay, so add and select your fixed support, and select your bottom portion. Okay, so the nodes have been selected. Now assign to selected nodes. Yes, assign. Yes. So all the supports have been assigned. So go to your isometric view. You can see here all our supports have been assigned with fixed support. Okay. Now our definition part. We have our definition part. Now go to your loads and definition. Okay, so we have completed our beams, columns, slab definition and assigned it to a geometry model. Okay, now we have to define for response spectrum analysis. First, we have to define our seismic load case, seismic definition. Okay, so this is a plus definition sign. Expand it, and here go to your seismic definition. Okay, select on seismic definition, add it. Okay, now here you are asking auto save yes, save yes. Okay, so you are asking your type of code, which type of code, is code you are dealing with. So you are, we are using, we have Indian standards of is 1893-2002. This is our earlier code, and we have a new code of 2016. So we are choosing here Indian standard 1893-2002. Okay, so after selecting your is code 1893-2002, we have to click on generate option. Okay, here generate, we are considering our in our problem we have our Shillong building is located in Shillong, so we have a zone of Shillong as 5. So select your zone as 5. and its design seismic factor is zone factor is 0.36. Okay, automatically we have a zone 5, we have a 0.36 values. Okay, so we are using our spatial RC movement resisting frame SMRF. Okay, so choose your SMRF building as here we have our spatial reinforced concrete movement resisting frame SMRF of response reduction factor of 5. Okay, and importance factor of all other general building, we have important buildings as 1.5 importance factor, and of all general building we have a 1 importance factor. So response reduction factor and your importance factor all general building, we have a response reduction factor value importance is that we have our R value, that is response reduction factor value, is the factor by which your base shear induced in a structure is reduced to obtain the design base shear. Okay, so it is helpful in reducing your base shear. Okay, so we are considering as MRF of response reduction factor 5 here, and in all general building we have our importance factor of uh, 1 here. So here it is your important factor, so select on your 1 and go to your other parameters like rock or soil depth. We have in a problem like medium soil we have to choose, so we are using our medium soil, and structure type is RC frame building, no problem. Damping ratio is 5%. Yeah, damping we have using a 5%, so generate it. Okay, so here you can see the properties. The zone is 0.36, response reduction factor is 5, and your importance factor is 1. Okay, and your damping ratio is 5. No, not 5, it is 5%. So it is 0.05. Okay, so change it. Now add it. Okay, now the seismic part, we have to add a salvage factor. Okay, so for salvage factor, go to a salvage factor 1. We have a salvage factor 1, add it. Okay, now go to your floor weights. Floor weights. Okay, and again, here you are using a floor weight of pressure of 12 kilonewton per meter square as dead load, with a range of 0 to up to the height of 14th floor, I think. So up to the height of 14th floor we have a 42 meters height, and on 15th floor we have a roof. So the dead load value in our problem is 10 kilonewton per meter square for the roof. Okay, so we are entering our values individually. So for pressure of 12 kilonewton per meter square, 12 kilonewton meter square, we are defining our y range value, that is the vertical value. So it is minimum is 0 meter and maximum is 42 meters. So for 42 meters we are assigning our pressure of dead load 12 kilonewton per meter square. So add it. Okay, so here your pressure value is added. Okay, it is a positive. Yeah, you have to remember in this seismic, you keep your values in positive. So because we are dealing in here in weights, and the mass of the structure is cannot be negative. So we are only dealing in our seismic definition part. We are using our plus sign values. So pressure is in plus sign value. Okay. So in Y range again, our for dead loads of 10 kilonewton per meter square, we have defined a Y range value of on the 15th floor, like if I'm considering 42.5 meters, it is of 45 meters, so 10 kilonewton per meter square is applied. So add. Okay, now again for floor weights we have our live loads, this is our dead loads. Okay, so 12 kilonewton per meter square for a floor of 14, and 10 kilonewton per meter square for a floor on load on roof. Okay, now we have to impose our live loads also. So for live loads we have a criterion IS code book, that is for imposed load of more than 3 kilonewton per meter square, we are imposing our live load on the structure as 50%. Okay, so our live load value is 4 kilonewton per meter square. So we are not using 4 kilonewton per meter square, we are adding to it 50%. So here we are using 2. So 4 kilonewton per meter square, 50% is 2 kilonewton per meter square. Okay, so it is applied for a Y range of 0 to 42 meters, okay, for all the floors. And on the roof we have our live load value different, so add it here, again add it. Okay, now we have our live load on the floor, that is your 1.5 kilonewton per meter square, but it is less than 3 kilonewton per meter square, so we are imposing it to 25%. So 1.5 25% is 0.375, so 0.375 kilonewton per meter square, which is to be applied on roof, that is 42.5 meters range to 45 meters. Okay, so if we are considering here the range of 42.5 to 45, it means whatever the floors are coming in this range, it will be applied. So we have our 42 meters on 14 story, and beyond 42 meters we have our next roof level. So it is, that's why I'm selecting here 42.5. You can put your value of 43, 44, 45, or 45, no problem. Okay, this is up to you. Okay, so add it. Okay, now seismic definition part is complete, close it. Okay, so all the dead loads and all the live loads are defined here, and seismic definition part is complete. Now this time we have to select your or develop your load case details. So select your load case details, add it. Okay, so now first we are dealing with our dead and live loads. Okay, so here choose your dead and live loads, dead and live loads. Okay, you can name it as dead and live loads. So add it, close it. Now select dead and live loads, now add it. Okay, okay, now we are using here our values of salvate here in our y direction. Okay, now these are simply similarly you did in your pre earlier tutorials or earlier projects. Like you, if you are doing your dead and live load in Staad Pro, then you have to choose your y value in negative sign. Okay, but in seismic, you have to make sure that your loads applied on a structure are always in positive manner. Okay, and we have to keep in mind. So here we are defining our dead and live loads. So here salvage factor of -1 is applied already. So add it here. It is added here. Okay. Now we have to apply our dead load of 12 kilonewton per meter square in global direction y. So go to your floor load. Okay, so floor load here, your pressure value is 12 kilonewton per meter square for dead load. So here you are, I'm using minus sign, so minus 12 kilonewton per meter square. Okay, in y direction. Okay, because and it is apply for 0 to 42 meters height. Okay, it is a 14 story. So global y direction minus 12 kilonewton per meter square. So add it here. Okay, now again your 10 kilonewton per meter square is applied as a dead load on your story of 15, that is roof, that is 42.5, and it is maximum height is 45 meters. Okay, in global y direction, so added here, so it has been added here. And now for live load, okay, live load we have to add our pressure value again here. So for add live load of um, 0 to 45 meter live load, what of live load value is 4 kilonewton per meter square. Okay, so here we are not reducing it to 50%, because we are simply here added to a dead or live load. So here we are using our full value. Okay, so our value is 4 kilonewton per meter square as live load for a floor range of 0 to 42 meters. Okay, so add it, auto save, yes, here it should be added. Okay, now live load has been added, and again our on floor we have our live load value is 1.5 kilonewton per meter square for a y range of 42.5 to 45 meters. Okay, so pressure value of 1.5 kilonewton per meter square on the floor, it's to be added, yes, add it. Okay, close it. Okay, now we have completed our first load cases, that is dead and live loads. So salvage factor, y range, live load and dead loads, all the These are cell weight. So assign your cell weight the whole structure. So select your cell weight and assignment method assign to view. So assign it, assign yes. So cell weight have been assigned to your whole structure. Okay, you can see here. Okay, so this is your cell weight and this is your dead load on all the floors except roof. For roof we have our minus 10 kilonewton per meter square for a range of 42.5 to 45 meters, and for live load we have a value of 4 kilonewton per meter square. Okay, it is not imposing here 50%. Okay, I am considering here full load, that is my value was 4 kilonewton per meter square as live load on all the floors and 1.5 kilonewton per meter square as a live load on the roof. Okay, so I am considering here whole because I am dealing with dead and live loads. Okay, now first load case part is completed. Now select your load case details again. Now add your second load case, that is seismic. Okay, so select your loading type as seismic. Okay, now here you can change your name as seismic loads, SEIS, seismic loads. Okay, put your values and add here, close it. So here this is simply a folder. Now we have to add our load items in seismic load case. Now select your seismic load case. Now add your seismic load items. Okay, so add your seismic load item. Now here we are dealing with response spectrum analysis and in dynamic analysis. This is, you have to keep in mind that when you apply for multi-story building and for by response spectrum analysis, we have to be very sure that we have to apply our cell weight or all the loads, floor loads in all the directions, that is x, y and z direction, with a positive value, not of a negative value, as earlier we did while assigning your seismic definition of applying load, that is plus 12 plus 10 plus 2 and 0.375. Okay, so here again we are choosing a seismic load cell weight factor in all the directions. Okay, so our cell weight factor should be applied in x, y and z direction, so with a positive factor of 1. Okay, I already gave you the reason of why we are not using on negative sign, because in response spectrum analysis we are dealing with weights. We have to consider weight mass value, so mass cannot be negative. Okay, so that's why we are considering here as positive. Okay, so here factor as 1, self weight of in x direction added, here it is added. So again in y direction self weight factor 1 added. Okay, here it is added. Now cell weight in z direction, again here it is factor of 1, here it is added. Okay, so we have our cell weight factor x, y, z and direction. Cell weight has been assigned, added. Here it is not assigned here because we have a question mark. When we apply it on the whole structure, then a question mark will be removed. Okay, now choose your floor load again. So for floor load, we have to keep in while defining your seismic loads, we have to make sure we have to apply in all the directions, that is x, y, and z directions. So with a positive sign. Okay, so pressure value of 12 kilonewton per meter square is applied as a seismic load. This is important. Okay, so this part is important. I will tell you why it is important, because it is helpful in calculation of the seismic weights. Okay, so wi, which is, I will explain you tomorrow what is the significance. Okay, so pressure of 12 kilonewton per meter square this global x direction. Okay, for a y range of 0 to 42 meters. Okay, for 14 story height. Okay, now add it simply. So it is added here. Again in y direction it is 0 to 42 meters y range, added. Then in z direction 0 to 42 meter, added. Okay, so here these are added here. Now again for dead load of, it is asking for years, save years. Okay, now this is our dead load on all the floors. Now for dead load of 10 kilonewton per meter square on the roof, we have to add in x, y and z direction. Okay, so select your x direction and keep your y range value as 42.5 meters or 45 meters, whatever you want. You keep your minimum y range minimum value of 45 meter here and maximum value of 45 meter here. then it will automatically apply at the level of 45 meter, because we know we have our floor in 45 meters range. Okay, so apply a 10 kilonewton per meter square. Okay, not negative. Okay, I tell you that is always positive. So global x direction added. Again for global y direction, this is to be added. So in all the directions we have to apply our dead load and live load values, okay, to contribute the weight, total weight of the structure. Okay, so here we have added our dead loads of on all the floors and on the roof. Now we have to keep in mind our, that is, while applying our live load, we have to take our values of 50%. Okay, whatever our I have a live load. So we have our live load in our problem as 4 kilonewton per meter square. So 50% of 4 kilonewton per meter square is 2 kilonewton per meter square. So I am assigning here 2 kilonewton per meter square in all the directions, that is global x direction for a range of 0 to 42 meters. Okay, because we have 14 floors in this range only. Add it. Again in global y direction, add it. Again in global z direction, add it. Okay, so this is our live load. 50% live load have been imposed because we have a value of 4 kilonewton per meter square, which is greater than 3 kilonewton per meter square as per clause IS 1893 2016 of new code. We have our provision that we have to apply our value and 50%. So here we are considering. So again on roof we have a value of 1.5 kilonewton per meter square, and we have to impose to 25%. So it is 0.375 kilonewton per meter square in all the directions. That is minimum value is 42.5 to maximum value is 45 meters. Okay, this is our live load value. Add it. Again in y direction, add it. Again in z direction, add it. Okay, now all our dead load and live load values have been signed. Okay, so close it. Here you can see your seismic loads. So these are very important. Okay, now these are having a question mark. Now select your cell weight, next one direction, assign to view. Okay, it is taking some time. Stat is taking some time depending on the configuration of your laptop. Okay, so select your x1, then assign to view. Here assign. So assignment method, yes. Do you want to assign? Yes. So it is assigning here. Okay. Likewise, select your y range, cell weight in y1 direction, y direction. Assign to view. Assign. Yes. So it is assigning here. And again, select your. It is taking some time. Okay. Wait for some time. It is processing here. Once it is, and we will start. Okay, now select your z. Okay, yes. Now select your cell weight in z direction. Assign to view. Assign. Yes. So cell weight have been assigned in whole the structure. Okay, now we have to add our response spectrum case. So go to your seismic loads, select your seismic loads. Okay, now add here our response spectra case. Okay, so for go to your response spectra. Okay, this is a response spectra. Now we are choosing here code value of 1893 is 1893 we are using. Okay, so here you see the combination method. We have our combination method of how we have to calculate our values of modal masses. Okay, so combination of modes. So it is peak response quantities should be considered here and calculated depending upon what method you are applying. So here there is SRSS method, ABS method, which you will study in your earthquake engineering. And here this is a sum root square method, and here it is CQC method, that is the complete quadratic combination method. Here we are using your CQC method, okay, complete quadratic combination method. If our buildings have a closely spaced modes, okay, so it is preferred in this time. So choose your CQC method. for analysis. Okay, and keep your value in x direction and keep your value in z direction. Okay, and here these values should be calculated with help of your AH value, that is z by 2 into I by r into SA by g. From here it should be added here, but for our convenience we are simply adding it as 1. Okay, and here and also in 1. So because earthquake, the major response showing in x and z direction here, so I'm considering my factors in 1 as 1 and 1. Okay, for more details we will apply our value from with the help of AK value, that is AH value, z by 2 into I by r into SA by g. But for our convenience I am keeping my value as 1 here. Okay, of damping of 0.05, that is 5%. Okay, if I am not adopting here any scale, so it is automatically by default it is 1 here. So this is a CQC IS1 and 90. Now subsoil class, we have to choose our subsoil class as medium soil. Okay, so choose our medium soil here, and now edit, now close it. Okay, so here you can see the response spectrum command has been assigned. Now go to your materials. This is a materials. Okay, select your materials. Okay, now this is a material whole structure. Dialog box will open and it is asking your steel, aluminum or stainless steel, concrete. We have a concrete, so assign to view. This is your view and we are assigning here to whole view. So select your concrete and assign to view. Yes, assign. Yes, so the material has been assigned here. Okay, now all the commands have been and defined. So now we have to go to analyze and print option. Analyze and print option, no print, edit, close it. Okay, so analyze our structure. So run analysis, is asking structure has been modified, save it. Yes, save. Okay, so it will be doing their work. So we are looking for our zero errors. So here you can see all our loadings have been defined correctly. Okay, so we have zero errors. And go to your post processing mode or your output file. Okay, go to your post processing mode. Done. What we have to choose, we have to choose our dead loads, apply. Okay, okay, and also your seismic loads we are seeing here. So this is a complete analysis by response spectrum. Okay, so choose your beams here. Okay, this is how it is selected. This is a shear force diagram. Okay, in red direction, close it. This is a bending moment value. Okay, and here your plate. Okay, like this way we are analyzing our structure. And we go to your stat output file. This is the output file. We have our zero stiffness. Go to directly your results. What we have our eigenvalues here. So Staad will calculate our automatically our first 6 model cases. Okay, so by default it is utilizing our first 6 mode cases. Okay, so here we have our results of eigenvalue solution. I will explain you tomorrow. So these are spectrum load here in all the direction, x, y and z direction model weights. It is calculating here dynamic weight and missing weight, model weight after subtracting here. And here this is a peak story shear. Okay, this is a peak story shear. You can check your results and validate your results with your reference books. Okay, and this is a model based actions. Okay, and this is a participation factors. Okay, we are choosing here a total CQC, that is complete quadratic combination here. So we have a total value of base shear in kilonewtons as 14489 kilonewtons. Okay, these all our results. Okay, so let me tell you what does Staad do in the while calculation of base shear or design base shear, that the design literal shear force at each floor in each mode is computed by it, and with the help of empirical equation like AK multiplied by phi I k multiplied by PK into WI. Okay, so we assign our values, just already we assigned here WI value as user input values and AK value. Okay, that is I entered as 1, but in actual it will be calculated on the basis of Z by 2 into I bar into SA by G. Okay, so we have to input two values, and Staad utilizes the following program, like we have to provide our AK value, that is Z by 2 into I bar, and for input spectrum, and then program calculates the time period for first six modes. Okay, so here you can see these are the first six modes. So program calculate automatical time period, these are the time period, that is the cycles per second. Okay, this is a frequency, and program calculates again the SA by G for each mode of utilizing time periods and damping. For each mode we are considering here 5% damping, and the program also calculates the design horizontal acceleration spectrum AK for different modes. Again it calculates the participation factor, mode participation factor. Okay, so this is also calculated by the Staad for different modes. Again the literal seismic force at each floor is also calculated in each mode by the Staad. Okay, and all the response quantities for each mode have been calculated by the Staad, and by choosing our CQC method or the peak response quantities combined with complete quadratic combination in this example to get the final results. Okay, so this is all about the dynamic analysis by response spectrum method. Okay, so you go through this video, and if you have any doubt, so we will discuss tomorrow. Okay, thank you so much.